Okay, so last time, exactly a week ago, we were studying this theorem 4. Let's try to remember what we learned about this theorem. We are handling the situation where our vector b in our linear system is it can be any vector. So these four theorems, or these four items, are saying so they are specifying some characteristics when regardless of any b vector in this equation. So for any b value, if this equation is having always a solution, which is either just one solution or infinitely many solution, this situation is the same as basically when changing this augmented matrix. So we can form this kind of augmented matrix, and then let's assume that we changed it to echelon form or reduced echelon form, and then this part, which is corresponding to the left hand side of our equations. Okay, so for example, 2x plus 3y, 2x1 plus 3x2 equals minus 1, 3x1 minus x2 equals 5. Okay, in this case, this a part will become 2, 3, and 3 minus 1, right? In the case of b, minus 1 comma 5, right? So we are considering this kind of augmented matrix, and then suppose we change it or converted it to echelon form. Okay, and in this echelon form, so we do not care about what these values are, but in these echelon form, in this part, which corresponds to those coefficient values, if we have a echelon form like 3 minus 1 and 0 and 4. So in this case, although it's a little bit noisy but messy, but is it the echelon form? Is it echelon form? Yes, because we are seeing at each row we have two rows, and then we see the leading entry in each row here, right? And then we look in the below of each pivot, and then we see 0 here, right? And then this pivot or this leading entry is on the right right column from this pivot in the above row, right? So if you recall, we can have this kind of staircase shape, right? So this is basically an echelon form. And then this theorem says, regardless of what these values are, if we have a leading entry, or non-zero, the leading entry in the echelon form, that is, if we have a pivot in every row, okay, again, at each row, if we see or if we find the pivot inside of this part, and then we can guarantee that this equation has always at least one solution. Okay, so there is it is impossible to have no solution. Okay, so in this case, here the point is, suppose we have the same coefficient matrix of 2, 3, and 3 minus 1, and then now this coefficient was maybe 100 minus 5, for example, and then we will have 100 and minus 5. And then if we change this guy into echelon form, and then this part, this coefficient part will always be the same as this guy, right? So if you imagine the row reduction that we do on that matrix, we do not care about these values until we create some staircase on the left part in our matrix, which is our matrix A. Okay. So this theorem says, regardless of what these values are, for any values in this part, if A part has a pivot in every row, okay, in that case, we can guarantee that we have always at least have one solution or infinitely many solutions. Okay, then from the vector equation, we know that when the solution exists, it is the same as every vector B. It can be represented as a linear combination of columns of an A, right? So in this case, for any vector, 100 minus 5 or 2, 3 or 0, 0 even, or 1 minus 1, for any vectors, okay, all these vectors are linear combination of what? Those 2 comma 3 and 3 comma minus 1. So if you do some linear combination using these two vectors, you can always create any vectors that we are given. And this case is also the same as the last one, not the last one, the third one, of the columns of A spans our Rm. So the dimension of the B vector, 100 minus 5, 2, and 3, the dimension of these vectors are the same as the number of equations, right? Because we have two equations, that's why we have two numbers in the B part, okay? So we consider, so M is 2. So R2, when writing this R2, it means it's entire space, entire universe in the two that contains all the possible two-dimensional vectors. Okay, although of course they are in a real value domain. I mean, we are considering the real value. That's why we call this guy as R. Okay, so. So this situation also means that the linear combination of these vectors, and then considering all the possible linear combinations, and that's what we call span, right? So span means we collect all the possible linear combinations of the given vectors, right? So that is the span. So that span is exactly the same as the entire universe in two-dimensional space. Okay, so that's when, for given any vector, so any given vectors, that is always belonging to the span of the given vectors. Okay, and again, that is the same as the situation where we always find the pivot after after converting this matrix into an echelon form, and then we have to be able to always find the pivots in every row in this A part. Okay. Questions? Okay, so to help you understand this theorem, I created some MATLAB code. Okay, so let's look at the code. So first of all, I created a matrix as a coefficient matrix. That has, so AA, So I created this kind of matrix. Okay. So these are the coefficient matrix. Not yet considering the b vector, which means how many equations do we have? Equation number, and the number of equation is 3 because we have 3 rows. How many variables? 4, right? Because it doesn't contain the b part yet. Okay, and then I created the augmented matrix AA underscore aug by just concatenating 1, 5, 3 as a additional column. To have something like 0, 0, 0, 0 and B kind of columns, okay, where we have the first non-zero entry in the last column corresponding to the B vector, right? So this kind of case is actually those cases that the theorem that we learned is talking about. Okay. So again, in this case, we can guarantee that this has always the solution, and it doesn't matter even if we change the b part as 100 minus 1 and maybe 2, yeah, and so on. So in this case of basically any vector b, we can guarantee that we always have a solution. Okay. Okay, and then the next case is this. So this is our coefficient matrix. Okay, so let's see. So let's look at the AA coefficient matrix. So it's 1, 2, 3, 4, 4, 5, 6, 7, and 6, 7, 8, 9. Okay, so if we change that and as a reduced echelon form, and then it will have this kind of value: 1 here, which are our 2 pivots, but the last row will have no pivot in A part. So this shows such 2 pivot positions in here. So it means in every row, I mean some rows doesn't have a pivot, right? So the first 2 rows have a pivot, but in the last row or the third row, it didn't have a pivot, right? So in this case, if we think of this kind of matrix, so the coefficient part is the same, and then the last column corresponding to B vector is set as 1, 5, 3. In this case, if we change them into reduced echelon form, in that case, we can now see some pivots in the last column, which corresponds to B vector. Okay, so in this case, as we saw in this example, so we are seeing some bad rows that have all zeros except for the last non-zero entry. So that corresponds to the equation of 0 equals non-zero, right? So that's when we have no solution. Okay. But so in this case, it does not satisfy the theorem 4 that we just learned. But in this case, let me ask one question. So in this case, we used 1, 5, and 3 as our B vector. And would it be possible to change this B value so that this equation has some solution? So in the case of B as a 1, 5, 3, we see that there is no solution. But is it possible? Yeah. So the question is, this equation has always no solution, or does it sometimes have some solution, depending on the B vector?
Or zero.
Yeah, so if this value 3 was carefully set as some value, so that this value will become 0 as well in here, right? Instead of just a non-zero value. And then the last row will 0, 0, 0, 0, and 0, right? So fortunately, we can kind of avoid this kind of situation by just having 0, 0, 0, 0, and also 0, right? So that way, in this case, we can sometimes have the solution, but it's completely dependent on what B vector that we have, okay? But again, this theorem, okay, this theorem is saying, the situation that this theorem is talking about is regardless of any vector B, okay? So these should be true for any vector B, okay? Questions so far? I think I created one, maybe two more examples, and let's see what that is. So these are the two examples. So these are A matrix. So how many equations do we have? 3, right? How many variables? 2, right? In this case, we have a pivot in here, but the last row doesn't have a pivot. And so for some B value, 1, 5, 3, it doesn't matter, even if it's like maybe 100. So it will do the same result. It will give the same result like this, right? Okay. So in this case, we have a pivot in the last row, the last column, right? Which corresponds to the vector B part. So in this case, yeah, it is not satisfying the situation of theorem 4. Okay. So as we saw here, let me ask one question. So suppose we have 3 equations and 2 unknowns. So these are our coefficient matrix A. So in this case, is it ever possible to satisfy the theorem 4 using this number of equation and number of variables? So in this case, yeah, so let's think about the possible cases of pivot positions, and then we consider this B vector. Yeah, but in this case, the pivot can exist per row. Only one pivot can exist per row, right? And so we have 3 rows, and we have, suppose we have a pivot here, and then the next pivot as here, and then what about the 3rd row? So in this case, can we have a pivot in the 3rd row in these 2 columns? It's not possible, right? Because if we have a pivot here, then we have to see zeros here, right? So that's the definition of a echelon form, or kind of reduced echelon form. And then if we see pivot here, and then we have to see also 0 here, right? So the first 2 rows had a pivot in A part, but unfortunately the last row didn't have a pivot, right? In this case, it cannot satisfy the situation of theorem 4. So that means yeah. So that means all the three are false as well. So A didn't have a pivot in every row within A part, right? So the last one was false, and thus we cannot guarantee that this equation may not have a solution. So we cannot guarantee that this has always a solution. So it's really dependent on the B vector. Sometimes it will have some solution, but sometimes it will clearly have no solution because this guy is false and all are in the same fate or destiny. So this has to be false as well. And then these two are also false, which means some vector B is not a linear combination of columns of an A, and also the columns of an A does not span Rm. So here, what is Rm? So this is the dimension of vector B, and then in this situation, the vector B is three-dimensional case, right? And then, what kind of span should we consider? The span should involve those two vectors, this guy and this guy. Okay, so we have two vectors that we use to span, right? To consider all the possible linear combinations of these two vectors, and then those two vectors cannot fill up the entire three-dimensional space. Okay, so it is really obvious, and this is the example that we use these kind of fingers. So the two fingers in our three-dimensional space. By using just the two fingers, we can only span this very thin plane, right? So it is possible that B vector can exist outside of our span, which corresponds to no solution case. Okay. And then what about the other case? So we have, so this is our A. So we have two equations and four variables. In this case, we are given four different vectors, right? And then, what is the dimension of the vector B? It's R2. So we are living in really two-dimensional space, and then we are given like four vectors, okay? And then in that case, suppose we have a pivot here, and then pivot in here. In this case, in every row, we have a pivot, and so, yeah, it is the case that we can guarantee that we always have a solution, and also it means using these four given vectors when considering all the possible linear combinations, and then it will fill up entire R2 or entire two-dimensional space. Okay, then let's think about the same case, but now we have pivots here, but no pivots in the second row at all. So in this case, because second row doesn't have a pivot, so it makes the situation of theorem 4 false, right? So in that case, depending on the vector B, sometimes we have no solution at all, right? And in this case, it's kind of counterintuitive. So we are given like a quite sufficiently large number of vectors. So we are given four different vectors. So first, and like this, right? So given given four vectors, when spanning those four vectors, it doesn't cover the entire two-dimensional space. So that's what this situation means, right? So in that case, I can give you some example corresponding to this case. So let me ask you guys a question. So the first vector is a 1, 3. So I'm gonna fill up the remaining 6 entries in this matrix A. And then the first vector is a 1, 3. So which means we have a two-dimensional vector and 1, 3. So we are given this vector, okay? And then what should the second vector be when we have 2 here? So again, the situation is we don't have a pivot in the second row, and it means the span of these 4 vectors cannot cover the entire two-dimensional space. Okay, so we are given just a 1 vector. Okay, and then using only this, the span will be something like this, right? By stretching freely those 1 vectors. Okay, we add another vector, and that vector, when considering that vector, it still doesn't cover the entire two-dimensional space. And what should this value be? It should be 6, right? Why? The point is we have to have this vector to be on the same line in this span of the first vector. So that's when the span of these 2 vectors are still not covering the entire two-dimensional space. What if this value was maybe 2? Okay, in this case, 2, 2. And then we now have these 2 vectors, and this is when we cover the entire two-dimensional space by using these 2 vectors, right? So it means, yeah, we have 2 and 6, and what about -1, -3, and maybe 3, 9. Okay. And also, yeah, so in this case, it cannot cover the entire two-dimensional space. And let's think about the original set of equations corresponding to these. So in this case, x1, 2x2, minus x3, and 3x4 equals something. And also the second equation is 3x1 plus 6x2 minus 3x3 plus 9x4 equals something. So we are given these 2 vectors. And that's when the coefficients are exactly having the same ratios. So that when subtracting some multiple of the first equation to the second, okay, the second equation will completely become 0. Okay, except for the last one, of course. So in this case, if it was maybe, yeah, suppose it was 1, and then suppose the second value was -1. Does it have a solution or not? It does not have a solution, right? But we can still make this case having some solution. What is that value be? What is that value in this case? It should be 3, right? In this case, we are quite lucky, so that those 2 equations still give some solution. Okay. Yeah, and then yeah, let's remember some other things as well. So this is a kind of fortunate case where we have a solution, and then let me ask another question then. Do we have a single solution, I mean unique solution, or only one solution, or infinitely many solutions? In this case, do we have a unique solution or infinitely many solution? Infinitely many solution. And why? How can we check that? How can we identify that kind of fact? How can we know that? The conic equation is true. Okay. So using some paper position, we learned about the basic variable and also free variable, right? So if we can guarantee that, we always So we can if we can guarantee that, we at least have a one solution or infinitely many solution, and then it's time to check whether we have a free variable or not. So what was a free variable? After converting it to a reduced echelon form or echelon form, we have to see the variables that does not have a pivot. So in this case, we have a 4 variable x1, x2, x3, x4, and then the pivot the variable that has a pivot, which we call basic variable, is only x1, and x2, 3, and 4, they are all free variable because in those rows we do not see any pivots, right? So we have a free variable, and thus we have an infinitely many solution. Any questions? Okay. Now, so this chapter is about the matrix equation, right? And then let's use another so these are the coefficient matrix, and then these are our vector b, okay? And then if you imagine it's the equation version, it's simple. I'm just writing them into an equation form. Okay, and then we know this guy is converted into this kind of matrix, right? But still, in the case of a matrix equation, and then we can write this equation as a matrix times vector multiplication equals the vector b, right? So this was the matrix equation. Oh, is it true or not? Yeah, it was wrong. It should have x3, x4, right? And then what was a vector equation? What was a vector equation? Changing this guy into the linear combination of vectors. So 1, 3, 2, 2, 3, 1, 4 minus 1. Then x1, x2, x3, x4, and we all sum them up, right? So this guy should be the same as this guy. So this was the form of vector equation. So this guy is a matrix equation, and this guy is called a vector equation. Okay, then so these are one example where we have these coefficient matrices and the 3 variables, and then this can be decomposed as a vector equation form. Then also, yeah, if we just compute the product, then we will have this kind of a single vector form. Okay, then we know this guy, yeah, this type of matrix is called a identity matrix, right? So identity matrix is all ones in our diagonal entries and all zeros in the non-diagonal entries. And what was the characteristic of this diagonal this identity matrix I? So we multiply any vector x using this identity matrix, it will always give the same same vector x, right? Okay, and then in this matrix vector multiplication form, there are some theorems. So we have a matrix A, and then we have two vectors. And then if we add these two vectors first, and then multiply this matrix A, and then it is the same as multiplying matrix A times U and matrix A times V. Okay, so this result is the same. And then the next example is we have a matrix A, and then we have some scalar C, and then some matrix, some vector U. So we first scalar multiple, we obtain scalar multiple on the vector U, and then multiply matrix A. It is the same as this matrix times vector. And then we have the scalar multiple at the end. So these two results are the same. Then the proof is simple, so yeah, I'm gonna skip these, and I think that's that's it for chapter 1.4. Then let's move to chapter 1.5. Okay, so the first concept that we learn is this homogeneous linear system. Okay, so homogeneous linear system is a quite simple concept where we have always zero vector as our vector B. Okay, so we have some matrix A, and then our variable or unknown as x, and then we should have some vector B, right? But for this B vector, it should be always 0. Okay, in that case, we call that as homogeneous linear system. Okay, so let me just give an example of a homogeneous linear system. So this was our coefficient matrix. Then this is our augmented matrix. Okay, and then how can we change the value of 100? Maybe as -3. So what should these two values be? So if you did the homework and then understood it, then you guys should be able to answer this question. What should those question mark be? Okay, 33. Yeah, 33. Okay, and then we now have a -3 in the place of 100, right? Okay, so the coefficient matrix again is this, and then augmented matrix is this, right? So suppose this is our original equation, and then it's a homogeneous version of the equation is Okay. We will study what that relationship is. Okay, so suppose we have this kind of homogeneous equation, and then in this particular equation, we can always obtain one of the solutions that satisfies this equation, which is all 0, right? So if we just plug all 0 vector in this equation, we can always make them as true, okay? And also in this case, yeah, this is a one type of a linear system, and then this one, I mean, the possible scenario in terms of the number of solution is 3, right? So the first scenario is when we have no solution, and then we have only one solution or infinitely many solutions. And then in this particular case, the fact that we found at least one solution, although this is simple, but it's at least our one solution, right? When setting all x's as 0, right? So in this case, among the 3 cases, having no solution, one solution, or infinitely many solution, it is impossible to have no solution. So no solution case is not possible in this case, okay? So let's think about why. So we have some matrix A and then some matrix B to form our augmented matrix, and then the B part is always 0, right? So that's the definition of a homogeneous equation. And then when is our equation, or when is our linear system having no solution? So when changing it into some echelon form or reduced echelon form, we should find some columns like this, right? All zeros except for the last one as non-zero, okay? So the fact that this ax equals 0 has always have at least one solution of all 0, okay? That means it is not possible to observe this kind of column, this kind of row in our echelon form, right? So can anyone explain why this is true? So why it is impossible to see this kind of a row? Yeah. Right. Yeah, so we started with all 0 columns in our B, and then what kind of operations do we do in order to create, or in order to change that into echelon form? We have 3 different operations, right? Row interchanges and scalar multiples of a particular row, or row replacement that just multiplies some rows by some scalar value and adding it to some other row, right? So in these 3 operations, if the last column was initially all 0, and then even after any kind of these 3 operations, the last row will always remain as 0, right? So that's why it is impossible to observe all zeros except for the last non-zero rows, non-zero values. Okay, so so the fact that we always have this kind of a very easy solution of all 0 vector, okay, so that can be understood as kind of making it impossible to have no solution, okay. Okay, and then this solution in particular is called a trivial solution. So this is an official name of this solution of all zeros, okay, because it's so trivial to obtain. Okay, and then the question is now, the question is whether we have infinitely many solutions or only one solution. Okay, but we already found just one of the solution. So if we have only one solution, that will be our only solution. But the question is, do we have any other solution? Okay. Okay. So as we saw in as we discussed maybe about 5 to 10 minutes ago. So what determines whether we have only one solution or infinitely many solutions? Free variable, right? Yeah, free variable. So if we have a free variable in a part, and then that's when we have more than one solution or infinitely many solution. Okay. But on the other hand, if we have no free variable, and then that's when we have only one solution, and that solution will be that zero, exact zero vector. Okay, so let's look at some example. So suppose we have this equation, and this is called a homogeneous equation since we have all zero, right? And so our augmented matrix is like this, right? So we have this coefficient and zeros, and then we do some row reduction in order to have a solution. And then suppose we have this kind of a reduced echelon form where we have pivot here and also pivot here and no other pivot. In this case, do we have a free variable or not? Do we? Yes. What is our free variable among x1, x2, and x3? x3, because x3 doesn't have any pivot, right? Okay, and then as you did in your homework, we change it to these equation form. Okay, so the first equation will become this, and then the second equation this, and then the third equation will become this, and then the next step will be to have or to represent this solution as this x1. So we place the basic variables on the left, and then we move all the free variables to the right, right? So let's do so in this case. And then x2 equals 0, and x3 is our free variable, so that we can choose any values for this x3. Okay, so this was our kind of solution when we did our homework, right? Okay, and then we now learn one more trick. Okay, just one more trick from here. That trick is this. So I'm just rewriting. So for this solution set, we can now represent them as a vector of x1, x2, and x3. Okay? And then we just change it in this form. Some constant vector and our free variable. What should these three values be in this case? So still x3 is our free variable, which is our scalar, and then what should this value be? x1 equals 4 over 3 times x3, right? So it should be 4 over 3, right? Then what about x2? What about x2? So x2 doesn't have any x3 term, right? So we can simply fill that value as 0, right? And then what about x3 part? So this is the free variable itself that we use here. And so we can just place that value as simply just 1. Okay? Okay, so again, x1, x2, x3 can be written as 4/3 and 0 and 1 times x3. And so this is a kind of a vector equation type of form. So x3 is still any variable, I mean any value that we can choose, okay? And then this kind of representation give us a kind of new interpretation of this equation. So that is this. So we have 3 variables, which means those 3 variables are living in our 3-dimensional space, right? And then our possible solution for x1, x2, x3 is along the line that follows, that has the direction of this vector. Okay, so this particular vector, x1, x2, x3, and suppose this vector was something like this direction. Okay, and then our solution can be understood, so we can understand our solution as any vector along this vector. Okay, so it's a quite easy trick, right? Moving from here to here, right? So you have to be really familiar, or you have to train yourself for converting from left to right. Okay. And this kind of representation is called parametric vector equation or parametric vector form. And let me see if we have, okay. And then let's think about another example. So suppose we have, so we still deal with the homogeneous equation. So in this homogeneous equation, see. Okay, so let's think about this kind of a reduced echelon form. And then let's reconstruct the equations from these reduced echelon form. And then can anyone tell me what the equation should be? Minus x3 plus x4 equals 0. And then x2 minus x4. Okay, so this one should be always 0 because we are dealing with this homogeneous equation. So in this case, we change them into this form, x. So what is our basic variable? x1 and x2, because we have pivots in here. But what about these two? They have no pivots. So these are all free variable, and so we represent them in this form. Right? So this is really simple. And then now let's do one more trick that we just learned. Okay, so x1, x2, x3, and x4. In this case, so we use first our free variable x3. Okay, so we have a scalar here, and then what should the vector be here? So what are those 4 values in this vector? First of all, what should this value be? 1. What about the second one? So let's look at x2. Do we have any x2? No, right? What about x3? x3 is just itself that we use as our free variable, and so it should be 1, right? Then what about x4? x4 is another free variable that we don't have something like x4 equals something something, right? So we don't have such kind of thing. So it should be 0. Okay, and then it's not the end. We have another, we have second free variable of x4, and then we still do the same thing. So what should the value be here? It should be -1. What about the second one? x2. Okay, good. What about x3? 0. What about x4? Okay, great. Yeah, you guys are doing great. So this is our final solution as parametric vector form or parametric vector equation. Okay, and then let's see. Compared to this previous example where we have only one free variable, so you can think of it in this manner. So we have one vector for each of our free variables. So if we have one free variable and then we have one associated vector, we just create it in this place or here, right? And in in this case, because we have two free variables, we now have these two different vectors. Okay? So similar to the previous example, in this geometric kind of interpretation or understanding, it's like we freely stretch out this vector along this vector direction. Okay, we can freely change the length of this vector by changing this value of an x3. And what about this? So we now have two different vectors, just like this, right? And then we can stretch or shrink the length of each vectors, right? And that means the solution set for this homogeneous equation can be thought of as the span of 1, 0, 1, 0 and -1, 1, 0, 1. Okay, so this is our solution set, which is represented as a span of these two vectors that are associated with each of these three variables. Okay. Okay, so in this case, in this particular slide, we call these two vectors that are associated with each of a free variable as u and v. Oops. And then we now have a two free variable of x3 and x4 in this particular case, but we can just change it as just s and t. It's just a simple notation changes, and s and t are just freely chosen, so it can be any values. Okay, so this is when we have two free variables and thus two associated vectors. Okay. Okay, now it's time to think about the original equation, not the homogeneous equation. And what is the relationship between the solution sets of these two different versions? the original one and also homogeneous one. So in the example 1 that we solved here, so we have these equations where we have this coefficient matrix, but we considered all 0 cases, which is a homogeneous equation. But now suppose these vector b is non-zero, except that, but still this coefficient part is still the same. So that's the example 2, where we have the same coefficient, but now we have some non-zero b vector. Okay, then if we think about the process of changing it to reduced echelon form, okay, this is the result of the reduced echelon form, right? And this is the resulting b vector. And then if we compare this case with this homogeneous version case, or homogeneous version, then this part for reduced echelon form will stay the same regardless of the vector b. Okay? So the only changing part is this. So we still have the same representation or same expression, but the last part, or the right hand side, is some non-zero values. Okay? And then if we change them into the parametric vector form, it is almost the same, except that we have some constant vector, but still this part is the same. Okay, so it's like from this solution, our non-homogeneous case where we have non-zero b vector, and then we will have some constant vector in this place, but still the first part will stay the same because we have exactly the same free variables and their representations. Okay, so that's it for today, and we'll continue next Thursday. This Thursday.
I have questions. Oh, by the way, did you receive my email?
No.
No, I mean in the vacation. I sent it before I went to the airport. I sent you one email and you reply, I think.
Did I reply? Yeah. Okay.
Maybe in December.
Oh,
yeah.
Yeah.
Yeah, I have a question. When we can say it's linear combination, when I can decide if it's linear combination, because I cannot get it here.
You mean something like this?
Yeah, for this one.
This one?
Yeah.
Okay, so for any b, the fact that we have always a solution for any vector b, it means, so ax, which means, suppose we have like a 3 columns and then an x vector, and then even before considering b, this is a linear combination of these 3 vectors using the linear combination coefficient of x.
Linear, that means we multiply with x, it's like scalar.
Yeah, so b should be at least b should be able to represent it as this form. So that's when we can guarantee that we have a solution. So when b is represented as this form, and then that's when we have a solution for that b. Okay.
Yeah, thank you very much.
이름이 뭐였죠? 서윤지. 그러면 50, 4, 5, 6, 7, 57.
줄서 이영서 이영서
몇 번일까요?
이제
13번?
네.
안 부른 것 같아요.
아 예.
저 저번 시간에 메일 보냈는데
네, 네. 아, 그래. 그래. 네, 알았어요.
안재미 출석 때 안 보내주세요. 저기요 16번 안 보내주세요.
네.
제한 혹시 시간 없으신가요?
아니, 괜찮아요, 괜찮아요.
아 감사합니다.
근데 여기에 피벗이 있고요.
네.
여기는 0, 0이에요. 이러면 이게 B가 뭐냐?
아 예 근데 그거는
그러니까 이게 그 케이스예요.
이거는 근데 이거는 대신 근데 식이 세 개잖아요.
네.
근데 이게 00이어도 이거 두 개가 이미 있잖아요.
식이 3개인데, 그러니까 이런 거죠. 그러니까
이거
x
만약-
플러스 2y 이퀄 3이에요. 1이에요.
네.
2x
플러스 4y
5y 이퀄 5예요. 요거 두 개는 방정식이 있어요, 해가.
네 무조건
근데
있죠.
자, 세 번째가 3x 플러스 7y 이퀄 얼마야지 해가 있겠어요? 이거 두 개를 더한 거니까.
6이요.
6이면 해가 있어요. 거꾸로 6이 아니면 8이면 이 방정식 세트가 해가 있나요?
근데 이게 8이어도 그러니까 이게 무조건 이렇게 되는 거예요. 그러니까 이거는 무조건 해가 있잖아요.
아니죠. 방정식은 이 세 개를 다 만족을 할 때의 해를 따지고
그래서요?
네.
그래서 그러면은 0하고 0일 때는 무조건 해가
네.
많을 수도 있는데 그 중에서 이거를 이
네.
케이스일
그러니까
때
여기가 0하고 여기서 해가 많을 수가 없어요. 왜냐하면 베리어블은 두 개고
네네.
다 피벗이 있으니까 해는 하나 있거나 아니면 빤 게 있는데
네네.
이 B 값이 여기처럼 이제 6이면 해가 있는 거고 다행히. 근데 저게 만약에 다른 값이면 이제 없는 거죠.